On August 17, 2017, at 12:41:04 UTC, a gravitational wave signal designated GW170817 arrived at the LIGO and Virgo detectors simultaneously. The signal lasted approximately 100 seconds. It was produced by two neutron stars, each containing between 1.1 and 1.6 solar masses, each approximately 20 kilometers in diameter, spiraling toward each other over a period of hundreds of millions of years, losing energy to gravitational radiation, and finally merging in a collision that lasted milliseconds. The merger occurred approximately 130 million light-years away. In the galaxy NGC 4993, 1.7 seconds after the gravitational wave signal, the Fermi gamma-ray space telescope detected a short gamma-ray burst from the same location. Then, 70 observatories around the world, optical, infrared, radio, X-ray, turned toward the same coordinates and observed the aftermath. The event was watched in real time across every wavelength of the electromagnetic spectrum simultaneously. It was the most observed astronomical event in modern history. In the weeks following, spectrographic analysis of the light from the merger revealed something that had been predicted theoretically but never confirmed observationally. The collision had produced an enormous quantity of heavy elements heavier than iron, including gold, platinum, uranium, and dozens of others. Not trace quantities, enormous quantities. The merger produced approximately 10 Earth masses of gold alone. 10 Earth masses of gold. In a single event, in approximately 1 second. The gold in your jewelry, the gold in the electronics you use, the gold in every bank vault on Earth. All of it was produced in events like this. Neutron star mergers that occurred before the solar system formed, scattered through the galaxy, eventually incorporated into the cloud of gas and dust that became the Sun and its planets. You are wearing the remnants of a neutron star collision. That event, GW170817, was 130 million light-years away. Safe, distant, observable as a scientific curiosity rather than an existential concern. The question this video asks is different. What happens if a neutron star merger occurs not 130 million light-years away, but within our galaxy, within a few thousand light-years of Earth? Close enough that the gamma-ray burst, the gravitational waves, the kilonova radiation, and the high-energy particle flux are not a scientific signal to be analyzed, but an environmental event to be survived. The answer involves several distinct physical mechanisms, each operating on different timescales, each with different consequences for Earth's atmosphere, biosphere, and technological infrastructure. This video goes through each of them, in order, without reassurance. Before we continue, the gold in your jewelry was produced in a neutron star merger that occurred before the solar system existed. The specific merger that made the gold atoms in any specific piece of jewelry cannot be identified, but the process is confirmed. Every gram of gold on Earth passed through a neutron star collision. Drop a comment if that changes how you think about what you are wearing. To understand what a neutron star merger produces, you first need to understand what neutron stars are and why two of them end up in the same place. We covered neutron stars in an earlier video in this series. Their density, their magnetic fields, their surface gravity. Here we focus on the specific scenario of a binary neutron star system. Two neutron stars orbiting each other, and the process by which they eventually collide. Binary neutron star systems form when two massive stars in a binary star system, two stars orbiting each other, both undergo supernova explosions. The first star to exhaust its fuel collapses into a neutron star. The second star continues to evolve, eventually also collapsing into a neutron star. If the system survives both supernova explosions without being disrupted, which is not guaranteed, since each explosion can impart a velocity kick that unbinds the system. The result is two neutron stars orbiting each other. The orbital period of a newly formed binary neutron star system is typically hours to days. The two neutron stars are separated by distances comparable to the radius of the Sun or smaller, close by stellar standards, but not yet merging. They do not merge immediately. They cannot. They are moving too fast relative to each other, and angular momentum prevents immediate collision. But they are losing energy. General relativity predicts that any system of masses in orbital motion radiates energy in the form of gravitational waves, ripples in the fabric of spacetime that propagate outward at the speed of light. For most orbital systems, planets orbiting stars for example, this energy loss is negligible. For a binary neutron star system, the objects are so massive and their orbits so compact that the gravitational wave energy loss is significant. As energy is radiated away, the orbit shrinks. The neutron stars spiral inward. Slowly at first, over millions to hundreds of millions of years, then faster as the orbit tightens and the gravitational wave power increases. In the final minutes, the inspiral accelerates dramatically. The orbital period decreases from minutes to seconds to milliseconds. The neutron stars accelerate to significant fractions of the speed of light, and then they collide. The first binary pulsar system, two neutron stars in a binary orbit, one of which is a pulsar, was discovered in 1974 by Russell Hulse and Joseph Taylor using the Arecibo radio telescope. The system, designated PSRB 1913+16, was observed over the following decades as its orbital period decreased at exactly the rate predicted by general relativity for gravitational wave energy loss. The Hulse-Taylor binary provided the first indirect evidence for gravitational waves. Hulse and Taylor were awarded the Nobel Prize in Physics in 1993 for the discovery. GW 170817 was the direct evidence. The gravitational waves themselves, arriving at Earth 130 million years after the merger that produced them. The Hulse-Taylor binary pulsar, PSRB 1913+16, has been monitored since its discovery in 1974. The cumulative orbital decay, the total reduction in orbital period over 5 decades of observation, matches the prediction of general relativity for gravitational wave energy loss to within 0.2%. The system will merge in approximately 300 million years. Its observation was the first confirmation that gravitational waves exist as a physical phenomenon, even before direct detection was possible. The merger itself, the final milliseconds when the two neutron stars actually make contact, is the most energetically extreme event that the universe regularly produces. Not the most extreme ever. Gamma-ray bursts from collapsing massive stars can be more energetic. The Big Bang was more energetic. But among events that occur with some regularity in the present universe, neutron star mergers are at the top of the energy scale. In the merger, the two neutron stars, each containing more than the mass of the Sun, each approximately 20 kilometers across, collide at velocities of approximately 30% of the speed of light. The collision does not produce a simple combined object. It produces a rapidly rotating, highly distorted mass of neutron star material that may temporarily exist as a hypermassive neutron star before collapsing into a black hole, or may directly form a black hole, depending on the combined mass. The collision releases approximately 10 to the power of 44 joules of energy, comparable to the total energy output of the Sun over its entire 10 billion year main sequence lifetime, in approximately 1 second. 1 second. This energy is released in several forms: gravitational waves, neutrinos, a short gamma-ray burst, and the kilonova, a transient optical and infrared source powered by the radioactive decay of the heavy elements synthesized in the merger. The kilonova is the most visually spectacular component of a neutron star merger for a distant observer. It is also the component that connects the merger to the matter you are made of. The term kilonova was coined by Brian Metzger and colleagues in a 2010 paper predicting the observational properties of neutron star merger transients. The name indicates that kilonovae are approximately 1,000 times more luminous than classical novae, though significantly less luminous than supernovae. The kilonova is powered by the rapid neutron capture process, the R process, in which atomic nuclei capture neutrons faster than they can decay by beta decay. The R process requires an extreme neutron flux, a density of free neutrons so high that nuclei can capture multiple neutrons in rapid succession, building up to nuclei far heavier than iron. The interior of a merging neutron star provides exactly this environment. The collision ejects neutron-rich material that is literally composed almost entirely of neutrons, at velocities of 10 to 30% of the speed of light. As this material expands and cools, the density drops below the threshold for stable neutron star matter, and the neutrons begin to decay and be captured by nuclei. The R process proceeds. Within seconds, elements heavier than iron are synthesized in quantities that would take the entire population of stars in a galaxy millions of years to produce through other nucleosynthetic processes. Gold, platinum, silver, lead, uranium, thorium, iodine, which your thyroid requires to function, barium, strontium, all of them produced in the neutron-rich ejecta of a neutron star merger, in quantities measured in Earth masses, in timescales measured in seconds. The radioactive decay of these newly synthesized heavy elements heats the ejecta and powers the kilonova luminosity. The kilonova from GW170817 AT2017GFO was observed to peak in blue optical light within the first day, then transition to red and near-infrared emission over the following week, as the opacity of the ejecta changed due to the presence of heavy lanthanide elements. The transition from blue to red is a direct spectroscopic signature of R process nucleosynthesis. The lanthanides, the row of elements from lanthanum to lutetium in the periodic table, have extremely high opacity in blue and ultraviolet light, causing the kilonova to appear red as the lanthanide-rich ejecta expands into the line of sight. GW170817 produced an estimated 3 to 13 Earth masses of gold, 3 to 8 Earth masses of platinum, and significant quantities of dozens of other R process elements. The total mass of R process material ejected was approximately 0.03 to 0.05 solar masses. 0.05 solar masses of heavy elements from a single merger, in approximately 1 second of R process nucleosynthesis. This is where the gold on Earth came from, not from supernovae. Theoretical models of supernova R process yields have struggled to account for the observed abundance of heavy elements in the galaxy. Neutron star mergers, confirmed by GW170817, are now understood to be the dominant source of R process elements in the universe. Every atom of gold that has ever existed on Earth was produced in a neutron star merger that occurred before the solar system formed, somewhere in the galaxy, in an event similar to GW170817 between 4.5 billion and 13.8 billion years ago. The gold was dispersed into the interstellar medium by the kilonova ejecta, mixed with other material, eventually incorporated into the molecular cloud that formed the solar system, and ended up, via billions of years of geological and biological processes, in the veins of rock where humans mine it. You are wearing condensed stellar catastrophe. The identification of strontium in the spectrum of AT2017GFO the kilonova associated with GW 170817, was announced in a 2019 Nature paper by Watson and colleagues. Strontium is an R process element, and its detection provided the first direct spectroscopic confirmation that neutron star mergers produce R process nucleosynthesis. The paper used the X-shooter spectrograph on the Very Large Telescope in Chile, observing AT2017 GFO approximately 1.5 days after the merger. Strontium features were identified at wavelengths consistent with ejecta velocities of approximately 0.1 times the speed of light. Now let's move from the kilonova, which unfolds over days to weeks, to the component that is most immediately dangerous at close range, the short gamma-ray burst. We covered gamma-ray bursts in an earlier video. Here we focus specifically on the type produced by neutron star mergers, short gamma-ray bursts lasting less than 2 seconds, and what they would do to Earth at different distances. The gamma-ray burst from GW 170817, designated GRB 170817A, was weak by gamma-ray burst standards. It lasted approximately 2 seconds and was significantly less energetic than typical short gamma-ray bursts. The reason for its relative weakness is geometry. The jet of relativistic plasma that produces a gamma-ray burst is narrowly collimated. It is a beam, not an isotropic explosion. GW 170817 was observed off-axis. The jet was not pointed directly at Earth. We saw the edge of the jet, not its full power. A gamma-ray burst observed on-axis, with the jet pointed directly at the observer, is far more energetic. The energy difference between an on-axis and off-axis observation of the same event can be a factor of thousands. What does an on-axis short gamma-ray burst from a neutron star merger do to Earth as a function of distance? The answer requires considering several distinct effects: the prompt gamma radiation, the afterglow radiation across multiple wavelengths, the cosmic ray flux associated with the event, and the longer-term effects of the high-energy radiation on Earth's atmosphere. At a distance of 1,000 light-years, within the galaxy, within the range of possible neutron star merger events in our region, an on-axis short gamma-ray burst would deliver a fluence of gamma radiation to Earth's upper atmosphere comparable to or exceeding the estimates for the gamma-ray burst hypothesized to have caused the end-Ordovician mass extinction. The end-Ordovician extinction, which we discussed in the gamma-ray burst video, eliminated approximately 85% of marine species. It occurred approximately 440 million years ago. The proposed mechanism was ozone depletion from gamma radiation ionizing the upper atmosphere, followed by years of elevated ultraviolet radiation at the surface. At 1,000 light-years, an on-axis neutron star merger gamma-ray burst would produce a similar or greater ozone depletion event. The duration of the gamma radiation, approximately 2 seconds, is brief, but the energy deposited in the atmosphere is sufficient to initiate a photochemical cascade that depletes ozone on a global scale within weeks. The ozone depletion is not immediate. The gamma radiation itself arrives in 2 seconds. The ozone chemistry, the production of nitric oxide from nitrogen and oxygen in the upper atmosphere, and the subsequent catalytic destruction of ozone by nitrogen oxides, unfolds over weeks to months. The elevated ultraviolet radiation at the surface persists for years to decades as the ozone layer slowly recovers. At 300 light-years, closer, but still within the range of possible events in our galactic neighborhood, the gamma radiation fluence is approximately 11 times greater. The ozone depletion is more severe. The ultraviolet exposure at the surface during the recovery period is proportionally higher. At 100 light-years, the distance at which a neutron star merger would be considered a proximate event, the fluence is approximately 100 times the 1,000 light-year scenario. At this distance, the ozone depletion would be extreme, potentially stripping a significant fraction of the total atmospheric ozone column, and the ultraviolet radiation reaching the surface during recovery would be at levels lethal to most surface-dwelling organisms and most shallow-water marine life. The nearest known binary neutron star systems, the systems that will eventually merge, are at distances of thousands to tens of thousands of light-years. None of the currently known systems are within the potentially hazardous range. But the currently known systems are a small fraction of the total. Neutron stars are difficult to detect unless they are active pulsars, and the majority of neutron stars in the galaxy are not active pulsars. The total number of neutron stars in the Milky Way is estimated at approximately 1 billion. The number in binary systems that will eventually merge is a small fraction of that, but a small fraction of 1 billion is still a large number. We do not know how many binary neutron star systems are within a few thousand light-years of Earth. We know the ones that happen to be detectable as pulsars. The others are invisible to current survey technology. The rate of neutron star mergers in the Milky Way is estimated from a combination of the observed population of binary pulsars, models of binary stellar evolution, and the merger rate inferred from gravitational wave detections. Current estimates place the galactic merger rate at approximately 10 to 100 per million years, roughly one merger every 10,000 to 100,000 years. The probability of a merger occurring within a potentially hazardous distance of Earth in any given million-year period is small but not negligible on geological timescales. The geometry constraint, the requirement that the gamma-ray burst jet be aimed at Earth, is the most important factor in the hazard calculation. Gamma-ray burst jets are narrow. The opening angle of a short gamma-ray burst jet is approximately 5 to 15 degrees. This means that only a small fraction of neutron star mergers in our galaxy, those whose jet axes happen to point toward Earth, would produce a hazardous gamma-ray burst event at Earth. For a merger at 1,000 light-years with a 10-degree jet opening angle, the fraction of the sky illuminated by the jet is approximately 0.75%. Earth occupies a tiny fraction of the sky as seen from 1,000 light-years. The probability that a given merger's jet points at Earth is extremely small. This geometric factor makes a hazardous gamma-ray burst event from a neutron star merger extremely rare, probably rarer than once per billion years for events within the lethal range. Probably. The rate estimate depends on assumptions about the galactic merger rate, the jet opening angle distribution, and the fraction of mergers that produce jets, all of which have significant uncertainties. The Ordovician mass extinction occurred approximately 440 million years ago. If it was caused by a gamma-ray burst from a neutron star merger, then such events have occurred within the hazardous range within the last half-billion years. Once in half a billion years is not never. Stop here. The gamma-ray burst that may have caused the end Ordovician extinction, which killed 85% of all marine species, lasted approximately 2 seconds. The ozone depletion it caused persisted for years. The ultraviolet damage to surface and shallow water life continued for decades. 2 seconds of radiation, decades of consequences. If you had to choose the single most dangerous component of a nearby neutron star merger, the gamma-ray burst, the gravitational waves, the kilonova radiation, or the cosmic ray flux, which one? Drop your reasoning below. The gravitational waves from GW 170817, arriving at Earth 130 million years after the merger, were detected by LIGO and Virgo as a strain of approximately 10 to the negative 22. This means the detector's 4-kilometer arms were stretched and compressed by approximately 10 to the negative 18 meters, 1,000th the diameter of a proton. This is the sensitivity required to detect gravitational waves from 130 million light-years away. The waves themselves, at that distance, produce effects so small that detecting them required the most sensitive measurement instrument ever built, What would gravitational waves from a nearby merger feel like? The strain from a gravitational wave scales inversely with distance. A merger at 1,000 light-years, approximately 130,000 times closer than GW170817, would produce a strain approximately 130,000 times larger. The strain from a 1,000 light-year merger would be approximately 10 to the negative 17. Still extraordinarily small, smaller than the diameter of a hydrogen atom. At this strain level, gravitational waves produce no perceptible physical effects on macroscopic objects. The human body, buildings, Earth's crust, none of these would experience any detectable distortion. The waves would pass through Earth as if it were not there, producing oscillations in space-time geometry that are real but far too small to be sensed by any biological or mechanical system. Gravitational waves from even a nearby neutron star merger are not directly hazardous. They do not shake buildings. They do not produce seismic effects. They do not heat materials. They interact with matter through the tidal forces they produce, the same tidal forces that drive ocean tides. But for gravitational waves, at these strains and frequencies, the effect on Earth is immeasurable. For a merger at 100 light-years, one of the closer scenarios, the strain would be approximately 10 to the negative 15, still far below the threshold of any physical effect on matter. For a merger at 1 light-year, essentially within the solar system's extended neighborhood, the strain reaches approximately 10 to the negative 12. At this scale, some theoretical analyses suggest that very sensitive geological structures might register the passage of the waves. But even at this distance, the gravitational waves are not the primary hazard. The primary hazard from a nearby neutron star merger is not gravitational waves. It is electromagnetic radiation. The gravitational waves from a nearby merger would, however, provide warning. LIGO and Virgo can detect neutron star mergers at distances of hundreds of millions of light-years. A merger within our galaxy would produce a gravitational wave signal of extraordinary strength, detectable with essentially infinite signal-to-noise ratio, providing precise localization of the source and approximately 10 to 60 minutes of warning before the merger itself, as the in-spiral signal is tracked to completion. 10 to 60 minutes of warning that a nearby neutron star merger is about to occur? What can be done with 10 to 60 minutes of warning for an event that produces ozone-depleting gamma radiation? Not much in terms of physical protection, but the warning would allow orientation of the gamma-ray burst threat, determining whether the jet axis is pointed toward Earth within the first few seconds of the in-spiral detection. If the merger is on axis, if the jet is aimed at Earth, the warning comes from the gravitational waves. The gamma-ray burst arrives 1.7 seconds after the merger. The kilonova develops over the following days. The gravitational wave warning is the only warning available, and it comes before the damage, not after. The LIGO scientific collaboration and Virgo collaboration announced the detection of GW170817 on October 16, 2017, in a coordinated release across multiple journals and press conferences. The announcement included papers in Physical Review letters on the gravitational wave detection, Astrophysical Journal letters on the electromagnetic counterparts, and Science on specific observations including the kilonova. The total number of authors across all papers exceeded 3,500, the largest coordinated scientific publication in the history of astronomy. Beyond the gamma-ray burst and the kilonova, a nearby neutron star merger produces a third category of hazard that operates on longer timescales: cosmic rays. The merger produces a relativistic jet and a collimated outflow of high-energy particles. As these interact with the surrounding interstellar medium, they produce a source of cosmic rays, high-energy protons and heavier nuclei accelerated to relativistic velocities that can reach Earth over timescales of thousands to tens of thousands of years after the merger. Cosmic rays are not a prompt hazard. They do not travel in straight lines. They are deflected by the galactic magnetic field, scattered, and delayed in their arrival at Earth by the tortuous paths they take through the interstellar medium. The cosmic ray flux from a nearby neutron star merger would arrive gradually, increasing over thousands of years after the merger, and persist for tens of thousands of years. The elevated cosmic ray flux during this period would have two primary effects. First, an increased rate of ionization in the upper atmosphere, producing elevated levels of nitric oxide and contributing to ongoing ozone depletion, a slower, sustained version of the prompt ozone depletion caused by the gamma-ray burst. Second, an increased rate of muon production at Earth's surface. Muons are secondary cosmic ray particles that penetrate to ground level and deliver radiation doses to organisms. The muon flux from a nearby neutron star merger, sustained over thousands of years, would increase background radiation levels at Earth's surface. The increase would not be large enough to cause acute radiation sickness in most organisms, but it would increase the rate of DNA damage and mutation, with potential long-term effects on evolutionary trajectories and cancer rates over the affected period. This is a subtle effect. It is not the dramatic, immediate consequence of the gamma-ray burst. It is a background elevation in radiation that persists long enough to affect multiple generations of organisms across the affected ecosystems. The combination, prompt gamma radiation and ozone depletion from the burst, sustained elevated cosmic ray flux over thousands of years, creates a prolonged environmental stressor rather than a single catastrophic event. Life has survived such stressors before. The geological record shows that mass extinctions have multiple causes operating over multiple timescales. A nearby neutron star merger would add a specific, high-energy astrophysical stressor to the set of environmental pressures that life must navigate. Whether the result is a mass extinction, a significant but survivable disruption, or a relatively minor perturbation depends on the distance, the jet orientation, and the evolutionary adaptability of the organisms affected. At 1,000 light-years, on-axis, mass extinction scale event. At 1,000 light-years, off-axis, elevated radiation, moderate ozone depletion, prolonged cosmic ray flux. Significant, but not necessarily extinction level. At 10,000 light-years, on-axis, detectable ozone depletion, elevated cosmic ray background, no mass extinction. At 10,000 light-years, off-axis, background radiation increase, potentially undetectable by paleontological proxy records. The distance and geometry determine everything. The cosmic ray hazard from nearby astrophysical events was analyzed by Malott and Thomas in multiple papers between 2011 and 2019. Their modeling of cosmic ray muon flux increases from nearby supernovae and neutron star mergers found that events within approximately 300 light-years could produce muon flux increases of 20% or more at Earth's surface. A 2019 paper in astrobiology proposed that the elevated muon flux from a supernova approximately 2.6 million years ago, consistent with the radioactive isotope record in oceanic sediments, may have contributed to the Pliocene marine megafauna extinction that eliminated approximately 36% of marine species at the genus level. Let's return to GW 170817. Not as a hazard scenario, but as a scientific event, and what it taught us about the universe beyond its immediate violence. The simultaneous detection of gravitational waves and electromagnetic radiation from the same source, multi-messenger astronomy, was the primary scientific achievement of GW 170817. It confirmed, for the first time, that short gamma-ray bursts are produced by neutron star mergers. It confirmed that neutron star mergers produce R-process nucleosynthesis. It confirmed the speed of gravitational waves to within 1 part in 10 to the 15th of the speed of light. That last measurement is worth emphasizing. General relativity predicts that gravitational waves travel at exactly the speed of light. Alternative theories of gravity, theories that have been proposed to explain dark energy or dark matter without invoking unknown components, often predict that gravitational waves travel at a speed slightly different from light. The 1.7-second delay between the gravitational wave signal and the gamma-ray burst, across a distance of 130 million light-years, places an extraordinarily tight constraint on the ratio of gravitational wave speed to light speed. The constraint rules out a large class of alternative gravity theories that predict gravitational wave speeds different from light speed by more than 1 part in 10 to the 15th. A single observation of one event, 130 million light-years away, eliminated dozens of theoretical frameworks that had been under serious consideration in the physics community. GW170817 also provided a new measurement of the Hubble constant, the rate of expansion of the universe. The gravitational wave signal provides an independent measurement of the distance to the source. The optical spectroscopy of the host galaxy provides the recession velocity. The ratio gives the Hubble constant. The value obtained from GW170817, approximately 70 kilometers per second per megaparsec, sits between the two existing measurements of the Hubble constant that disagree with each other in a tension that has been one of the central problems in cosmology for the past decade. The CMB-based measurement gives approximately 67. The distance ladder measurement gives approximately 73. GW170817 gives approximately 70, with significant uncertainty. As more neutron star mergers are detected by gravitational wave observatories, the Hubble constant measurement from gravitational wave standard sirens will become more precise. It may eventually resolve the Hubble tension, or it may confirm that the tension is real and requires new physics to explain. A neutron star merger 130 million light-years away is providing data relevant to the expansion rate of the entire universe. This is what GW170817 was. Not just a violent event, not just a gold factory, a measurement instrument, providing simultaneous tests of general relativity, nuclear astrophysics, stellar evolution, and cosmology in a single 100-second signal. The universe's most violent events are also, if you are positioned correctly, its most informative. On August 17, 2017, two neutron stars that had been orbiting each other for hundreds of millions of years finally merged. The merger lasted milliseconds. It released the energy of the Sun's entire main sequence lifetime in 1 second. It produced 10 Earth masses of gold, 8 Earth masses of platinum, and significant quantities of dozens of other heavy elements. It generated gravitational waves that were detected 130 million light-years away. It illuminated 70 observatories simultaneously across every wavelength of the electromagnetic spectrum. It was 130 million light-years away. The gamma-ray burst jet was not pointed at Earth. The kilonova was a point of light in the optical images, observable, analyzable, scientifically extraordinary, and completely harmless. The same event, at 1,000 light-years, on axis, would have been a mass extinction event. The gold in your jewelry passed through an event similar to this. The distance was sufficient. The geometry was favorable. The ejecta dispersed into the interstellar medium over millions of years, and eventually became part of the molecular cloud that formed the solar system. You are wearing compressed violence from an event that occurred before Earth existed. The nearest binary neutron star systems that will eventually merge are thousands of light-years away. None of the known systems are within the potentially hazardous range. The rate of mergers in the galaxy suggests that a nearby on-axis event occurs on geological timescales, rarely, but not never. The geological and fossil record contains the signatures of past astrophysical events. The end Ordovician extinction is one candidate. There may be others. The universe produces gold through the most violent process it has available. It scatters that gold through the galaxy and waits for it to be incorporated into planets and people. It has no preference for which planets. It has no preference for which people. It simply produces gold. And occasionally, the process is close enough to matter. One question. The gravitational wave detectors LIGO and Virgo would detect a neutron star merger anywhere in our galaxy with essentially infinite signal-to-noise ratio, providing 10 to 60 minutes of warning before the merger. If a galactic neutron star merger were detected tomorrow, and preliminary analysis suggested the jet axis was pointed in Earth's general direction, what do you think the appropriate global response would be in those 60 minutes? Not the Hollywood response, the actual, logistical, governmental response to 60 minutes notice of a potential mass extinction event. Drop your answer below. Next video. Exoplanets so extreme that they should not exist, but do. Planets where it rains iron, where oceans are made of lava, where a single day lasts longer than a year, and where the atmospheric chemistry produces conditions that no planetary formation model predicted. See you there.